let's compare what we got with known Lorentz transformation, right? We know Lorentz transformation with velocity along x or opposite x. So let us compare. So what does it mean, this matrix? That it means that x 0 prime, sorry, prime 0, this is, we can write answer for in terms of x. That this guy is equal this our matrix, right? Which I call lambda 0, 1 time, and it acts on x0, x1, x2, x3. And from here, we derive this simple linear relation. And now let's compare with what we know in standard Lorentz transformation, expressed through velocity. This is, now I will introduce explicitly C even. Okay, then from, let me pull this up, you will see this, and this down. Then comparing this relation, by the way, here you should consider x0 like CT, right? In this case, because I introduced a C. So let us compare, and we immediately get results that hyperbolic cos our beta is gamma, which is defined like this, inverse square root. Right? Sine hyperbolic beta is nothing but minus V over C. Same story in the denominator, right? And you could write hyperbolic tangents, which is ratio this over cos, sine over cos, hyperbolic, that this is minus V over C, and it's convenient to say that beta then is, oh, this is inverse hyperbolic tangents of V over C. Now remember this definition of cos and sine. You can see when V goes to C, gamma goes to infinity, then beta should go depending on sine of V plus infinity or minus infinity, right? So to get when you can see V goes to minus infinity, then beta should go to plus infinity. So beta goes to plus minus infinity when v goes to minus plus 1 to plus c. So you can see that this is certainly what I told before, non-compact group. This parameter beta changes from minus infinity to plus infinity. And this is very different from the case of rotational group, right? Now I was asked just after the previous class, what is the physical difference between, as I said, this matrix is not unitary unlike rotational, right? Okay, difference is huge even from physical point of view. As we know, generators connected with rotations, these generators are essentially operator of angular momentum, which is remarkable operator. It has real quantum numbers which are measured, right? So we can use eigenvalue of this operator to describe real physical quantity and wave function, right? Like even in hydrogen atom. But those operator, J with 0, like in this case 0, 1, they actually do not have, their eigenvalues are imaginary. You cannot use this eigenvalue to describe some observable quantity, right? At least immediately, maybe in some combination. So this is, and this is connected in turn that description of quantum numbers of Lorentz group more involved than in the application of this group in particle physics than rotational. But at this moment, we should stop just at this point. I would say, you still not ready to discuss with myself more deeply this issue. But it's huge difference. You can see already in that. Okay, now let me just show one also another interesting thing which will be kind of useful for you to accept something in the following discussion. And this is the following important observation. Let's do the following trick. This is Wick. This is name of famous physicist, Wick theorem, Wick trick. Let me. So let's take x0 imaginary actually. So let's consider x0 like imaginary quantity. It's called imaginary time. This trick extremely useful in quantum field theory, even for the calculation. It's called also Wick rotation and so on. And let's take beta. This is, let's act like mathematician. Sometimes we can do this. Imaginary this angle. Then let's substitute this quantity in our transformation written in the that corner, right, top right corner. Then we will get, oh, okay, also we should, some properties hyperbolic, very simple to check. Okay, use hyperbolic cos and right, I phi is just cos phi. Hyperbolic sine of I phi is nothing but I sine f. Then we will get in this our transformation becomes of the following form: x prime 4, just substitute x4 cos phi plus x1 sine phi and x prime 1 equal x1 cos phi minus x4 sine phi. And this is rotation so this is rotation in x1, x4 plane. So you can see that those boosts, if we consider this, can be considered a kind of analytic continuation used in complex analysis. That a kind of analytic continuation of Lorentz group is actually some rotational group. And this is group SO4, group which correspond to rotation in 4 dimensions, which is not surprising. We have x1, x2, x3, now x4. Okay, so let me even write this, that this is important. This analytic corresponds to SO4 group in 4 dimensions. Okay, now I will actually use it. So in order, of course, I cannot, as I said, spend too much time discussing representation of Lorentz group. You should believe some points I will tell. I will give reference to some text if you want to study this in more detail. But this, you will see, will be very useful. Now, point here is that it's quite easy, I will show this, to describe all representation of SO4. And then you already understand that Lorentz group connected with this, we will describe representation of Lorentz. This will be our strategy. Okay, so let's go to do this. So let's consider SO4 group and its representation. Okay, so its generators you can get from actually Lorentz group. And its generators are, let me just describe this. So now I will use only Latin indices, no Greek, to distinguish from Lorentz group. Now this guy A, B is 1, 2, 3, 4. And what is important now, we do not distinguish between upper and lower. XA upper equal XA lowercase, same for derivative. And of course, we should our metric, Lorentz metric, to replace by simpler Euclidean metric in 4 dimension, just Kronecker, delta AB. Okay, so we have this. Now, let me consider, yeah, okay, maybe I should start from here, right? All right, yeah, it will work. Yeah, I will kill it. Oh, sorry. Okay, now I will write commutator, so algebra Lie, and you will see that actually it's not difficult to describe representation of this group. Okay, so commutator is this. It's similar to that in Lorentz group if you compare what I wrote before, but now different metric. Okay, I could write usual parentheses. One, two, three, four, there. Right. So we have this commutator, and its 4-dimensional representation, which satisfy this stuff. Also, you should know. Is this JAB CD equal I delta, I will write in this form, delta D minus delta A D delta B C. Now let's do the following trick. We have 6, of course, generators because it's anti-symmetric, right? You can see with respect to AB, like in the case of Lorentz. So divide 6 generators into 2 groups. this guy, ij, and ij1 to 3. So this is a kind of usual rotation connected with 1 to 3 axis. On the other hand, another 3 connected with 3 other planes, 4, 1, 4, 2, 4, 3. Right. It's still, so we wrote this. Introduce now a new combination for generators. Introduce ji, which is 1/2 epsilon, this antisymmetric jk. So it's important we have summation over jk, right? Because they are repeated. And this is 1, 2, 3. And let us introduce ki, which is even simpler definition, 4i. Okay. Now we actually can consider commutators for those 6. Let's consider commutator for those new. And we get this, ji, jj, exactly like in the case of usual rotational group, of course. Then commutator j and k have, by the way, similar form. If, let me write this, k, k. Okay, it's not surprising because this guy k with respect to usual rotational group 1 to 3 is vector. This guy does not transform with. And those guys also, its angular momentum are vectors. Actually, they pseudo vectors, but they transform with respect to rotational group like vector. So it's not surprising. And the last one is this. Maybe I k, I, k, j equal e epsilon I, j, k, and j, k. Where are we going? You will see in a moment. Last, introducing. Introduce now the following combination. Mi plus ki 1/2 and ni their difference. Now take commutators for those guys. Then they're quite nice. Mi, mg, same like for j. Now, ni, ng, same like for rotational group. and k. You see, same. And the last one, attention. Those m and n commute. And this is quite remarkable. What does it mean? It means that we actually, yeah, use this. Let me, okay. I could write. It implies that SO4, is a direct product of two rotational groups connected with M generators, connected with N generators. But this, of course, we know it's same. It's connected with SU2M, you can also say, and this is with SU2M. But anyway, two rotational groups. What does it mean? It means that now we know all representation of SO4, because point is that it's known in theory of group that for such a construction, all representation of SO4 are just given by direct product of representation of this guy and this guy. So you just could consider very easy, you can describe all representation. Let's do this. We know all representation for rotational group. They are connected with angular momentum, quantum number, right? So S, what do you like more, SO3 or SU2? Actually, do you know this relation that SO3 and SU2 are some? Okay. So, okay, let me use all representation. Can be characterized by one all irreducible representation by one number, M. So we can write M over 2, and M is 0, 1, 2, 3, 4, infinite. So each M define irreducible representation. For example, M equals 0. This is invariant representation, trivial representation. Nothing changed in this case under rotation. It's scalar. Take M1, you will get 1/2. This is spinor, which we know in quantum mechanics. 1/2 representation described two degrees of freedom. Spin up and spin down. So actually dimension each is M plus 1. For each representation with M, it's M plus 1. For example, for M equals 0, this is 1. Just 1 degrees of freedom, scalar. For spin, 2. Now take M2, we will get 3, and this is 1, this is vector, right? Vector has spin 1 and 3 degrees of freedom. Plus, up, plus 1, down, minus 1, and 0. This is, again, angular momentum. So we know this. This is nice. Same story for, of course, N, but this is different vectors from different space, because you see they commute. It's like two spaces. And we independently could, and dimension N plus 1, right? then representation of SO4 are given by those two numbers. M2 and 2 with dimension m plus 1 times n plus 1. Okay, it's enough for us. We just use this in order to understand better description of representation of Lorentz group. Okay, so you can see SO4 is very simple group. Actually, this fact played important role in the discovery of grand unified theories. And Howard Georgia described nicely in some of his lecture. I believe it up somewhere. I heard it in Japan, just this Yukawa Tamanaga symposium he gave historically, how he came to that. But this is quite important. Anyway. Okay, now we are ready to understand, not to derive everything for Lorentz group. Here we essentially derive something, right? But for at least accept what I say, I hope you are ready, okay? So now let's return some questions, first of all, please. No, SO4 compact. But you see, in this, look here, our transformation, which was non-compact, it became rotational, compact. So SO4 is simple group. And this is connected with two compact groups. You can see with two rotations, right? Oh, with two rotational groups. So it's compact group.
We can basically transform a non-compact group to compact.
Not transform, I would say, yes, in a sense, yes, by using analytic continuation. We did here something unusual in principle from physics, at least, that now we consider imaginary time, right? But this group exists itself, right? If you know nothing about Lorentz group, it's, as I said, it's used in grand unified theories, right? So point is that, of course, when we work with real space-time, Lorentz group is Lorentz group. You cannot consider imaginary time. But it's useful mathematical trick, right? By the way, Hawking believes that it's not a trick. He believes that real time is imaginary. And what we call time, this is our manifestation of our ability not to see imaginary time. We somehow introduce this interpretation. He believes that Euclidean field theory with imaginary time, so-called, is more fundamental than field theory with real time. So you see, there is a lot of things to discuss, but let's go. Okay, now representation of the Lorentz group. We can work here, right? Let's repeat these steps, we introduce new generators. Introduce new generator. Okay. First of all, rotational subgroup. Let's work with this subgroup. So we had these guys. One, two, three. But by the way, we now in Lorentz group, so in principle, we distinguish between upper and lower. Be careful with that. And remember, for spatial, actually, G is -1. But, okay, we are doing. And introduce, so we transform in these guys. Similar what we did for rotational 1/2. Okay. So it means actually, right. We have this. I even, this guy corresponds to the following. J1, they're actually a little bit different than in the case of K. That doesn't matter. Okay, for example, I corrected my typo in the beginning of this class. I put here minus because in that case I used already grad and so on, kind of a Euclidean variable. Here is plus, no minus, but anyway, if I want to put this guy down and this guy down, then you should put minus here. And then you could consider derivative because this guy is derivative with respect to lower index. But if you want to consider derivative with respect to higher, you should put down and minus. But anyway, we have this. And we have not K, but in order to distinguish from SO4, K bar I, which is J0 I, and this is this. Okay, the D I minus X I D 0. And I, of course, 1, 2, 3. Okay, now let's let me write commutators for this guy. Okay, I believe. Okay, it's better to see. Maybe I can do this. No. Still not got to use this. Yeah, we can use it. Okay, so we stop on this stuff, right? So Lie algebra for this Lie algebra means just commutator. This guy, usual rotational. You can do this by yourself. Because we know all commutator I wrote in the very beginning of this class for all these guys. And the last, okay.
Yeah.
Oh, sorry. Yeah, just one moment. This is wrong. This is the same as, right, sorry. Yeah, thank you. Sure. This we should write, this I wrote, and the last one, 2K. Okay. Now where we have, just to compare, please write this stuff and let us compare with what we had in SO4 before. You see, this is same. This is actually same, essentially. But this guy has different sign. Here, plus KKJ. But in our case now, where it disappeared? Here, minus. Right. Oh, yeah, it's good question. It could be right. Okay, let me exactly. Yes. This is I, right. This is I, right. This is I. This is I, right. Okay, now let's.
It has epsilon.
Oh, yes, guys. Oh, my. Of course, thank you. Sure, this is bad. It's not typo, but error. Certainly, minus. Right. It's like that guy also. Okay, anyway. That guy also had, of course, epsilon. Yeah. You see this. Compare this and this. Only different sign now for SO4. Okay.
What does this difference mean?
We will see. We will see. Of course, that it's not SO4. If it were the same, then we would prove that Lorentz group is equivalent, right? But it's not. Now let's go. Then we will see what we can do. Okay. So only different sign. Introduce now those guys, analog of M and N, but I call bar them. Now attention and we will get answer to your question. What is difference? What does it mean? And n I 1/2 okay. Now we will get, and then I explain what is going on. Now we will get very nice commutation relation. Like in SO4. But this sign is crucial. Still, there is difference. We are coming to that. You see, we got again, like we got two groups, two sets of operators, M bar, N bar, connected with some, it seems, rotational group, but something wrong. And it could not be like that. And it's connected with introducing here I. And this is in turn connected with this minus. Point is that algebraically, I said this, but let me emphasize again. It's algebra. You could consider any linear combination of generator, but only with real numbers. When I put I, it's not already Lorentz group. It's a kind of analytic continuation of Lorentz group. And it's in turn connected with this minus. And in turn, it's connected with what I did here when I introduced X4 and imaginary time. But math, good math, sometimes use it. You use something new, you got something you maybe don't understand first, but then you recognize that you could use this for the description of representation. And actually, it was done in this way by mathematicians. So they recognize that knowing the structure of analytic continuation of Lorentz group, it can be used to describe representation essentially like in the case of SO4. So it's not true, of course, that Lorentz group can be presented like direct product of two rotational groups. It is not correct. It's not true. But it's useful, and one can prove, of course, we will not do because I cannot. I should study for that. But this is works of mathematicians like Naimark, Gelfand, and I give reference in the end to the text. But main point is that you should believe me, maybe you already, that you could use still this structure of analytic continuation to describe all representation, finite representation of Lorentz group by again two only numbers. But of course now it's but in this case you cannot talk. So one can use this construction finite actually. Describe finite representation. So this guy take value as before in SO4, 0, 1, 2, 3, and its dimension, their dimension are m plus 1 times n plus 1. Moreover, representation n over 2, m over 2 is complex conjugation of m over 2, n over 2. We will discuss it, especially will be important in the case of fermions, chiral fermions, left-handed, right-handed. But let me just indicate some interesting representations and simplest. This is Lorentz group. 0, 0. This is m equal 0, n equal 0. Scalars, like Higgs boson. Okay, this guy. M equal 1, n equal 0. This is 1/2, 0. This is left-handed chiral fermion. Weyl, who was first to consider them Weyl fermions. People thought that neutrino are like them, but now we know that neutrino has a mass, so it's more complicated. Still, it's quite important. Now, m equal 0, n equal 1, 0, 1/2. Right-handed. Weyl fermions. You see, by the way, you can see from what I said, not proved, that this representation is complex conjugation of left-handed, because it's 0, 1/2, this is 1/2, 0. So I said that representation n over 2, m over 2 is complex conjugation of m over 2, n over 2. So this is their relations, quite simple relation, actually, between them. Now this guy, m1, n1. Of course, dimension, let's consider dimension 1 in this case. In this case, dimension 2, because we have m plus 1 over n plus 1. This is, of course, also d2. So two-component neutrino has, massless neutrino. m1, n1, 1/2, 1/2. 4 vector. what I would say, yeah, okay, something like 4-vector field A mu connected with photon. There is subtlety photon is massless, but anyway, it's still valid from the point of Lorentz group, yes. So it's 1/2, 1/2. Dimension 4, 2 times 2, 4, like should be. Okay, apparently, now question, what is the representation for gravity field? And this is G mu x, right? I will formulate the answer, and we will start from that next time. What is the representation for the gravity field this is tensor, of course. Okay, let us consider this guy with head to distinguish from our Minkowski metric, okay? G mu nu, and it's, of course, depends on x in general case. And this is question. And answer is that this guy is in direct product of those representation 1/2, 1/2, 2-vector representation. But today I will not consider this. I will start from that. Yeah, so it seems maybe here. No, okay. We can this work out. And I will finish. Not finished, but I will answer your question if you have. We could discuss, because it's also important to interaction between us. Answer is, it is in so you should consider direct product of 2-vector representation, you will get tensor, but I will discuss this in details next time. So actually, this is reducible representation. One should select anti-symmetric, part symmetric, and trace, and all this stuff, but it's enough, I believe. So let's maybe interact if you just go ahead with the questions you have. So maybe a kind of summary today. So it was introduction kind of in the Lorentz group theory, right? Let me actually give maybe somebody of you interested to study more deeply, then you could look long ago when I was much younger. I used this text in Russian, but it's translated, of course it was. And now all authors work in States. So, yeah, this is, I will write only the first one, extremely famous. He is over 90, but still at Rutgers University, Gelfand et al. It's called Representations of the rotation and Lorentz groups and their application. And this is Macmillan Company. I'm not sure that it exists at this moment, but certainly it's in the library. Quite famous book, New York. 1963. This is time of Beatles and me. Okay. Yeah, I believe. Summary, yes, that it was a kind of short, so we spent the whole day discussion of Lawrence group, and certainly we will use this. We will use all this representation many times in this class, and you should not be surprised of this types, the structure, double structure. And I try to show you that it's connected with simple structure of SO4. And sure, SO4 is connected through analytic continuation with Lawrence group. And it's not trivial. This is, I admit it, rigorous discussion of that stuff. But this is certainly outside this course. It would take a couple of months, 1 month for sure. Okay, so go ahead maybe with questions. If not, then yes, please.
The whole thing down here, is it for, I mean, for to make the PI Hermitian?
Sorry? Yeah.
The generator PI is Hermitian.
Okay, point is that in the case of rotational group, yes. In the case of rotational, everything is Hermitian. But point is that because I introduced K, my K bar is not, but I multiplied this guy by I, then it becomes Hermitian. You see, but this is in principle forbidden. It means that it's not already Lorentz group, okay? But K bar is Hermitian. But yes, please. No question. Okay. So this is, yes.
Just a comment. These representations for are irreducible.
This representation for fermion.
Yeah, irreducible.
Sure, sure.
And we will have that. Radical, we will have reducible.
Right. Right, exactly. We will get reducible. Also, by the way, I did not write. I should write. I will write. I will repeat this. Anyway, somebody wants. This is representation works only for massless fermions. But to get Dirac mass, you should consider the following representation. Let me write here, okay? Representation of this type. It's simple. So we have those two. Let us now consider not product, but so-called direct sum. And this is by spinor, by means two, this and this. Dirac, massive fermion. It's again reducible representation. So Dirac equation actually uses this. You should inevitably, in order to introduce mass, Dirac mass, to consider both this guy and this guy. So they both should be in the theory. You cannot get Dirac mass. You can get another one, so-called Majorana mass, but we will talk about that later. But what is called Dirac mass, famous mass of electron, mass of proton, you describe in this representation, by spinor representation. Okay? Yeah.
My question was that we do the analytic organization thing to construct M and N, which are Hermitian.
Numbers Mn, of course, they are even integer. So Mn take value 0, 1, 2, 3. This is just number. Okay. right? So they are real, right?
So what's the representation for a 0, 1 field? Is that the actual photon field because it's massless?
For which representation?
0, 1. Or 1,
0, 1.
Yeah.
Okay, we will get. It's actually tensor representation.
Yeah.
Point is that we will get it when I describe this gravity stuff, but I will, where is chalk? I can take a lot of chalk here. Okay, so this representation 1, 0, 0, 1, it corresponds to antisymmetric tensor. It has 6 components because this guy has 3 and this 3. Actually, famous F mu nu in electrodynamics. This is exactly this representation. This is stress tensor in electrodynamics, right?
So this 1/2 isn't the actual photon field because the photon field doesn't have.
No, point is that A mu vector, you have in electrodynamics, for example, you have both vector field A mu potential, which is connected with this representation. But also you have stress tensor F mu nu, which is, of course, expressed through D mu, A nu minus D nu, A mu. And it assigned to this representation. Okay, so it's automatically. So you have both, but they are different. You see, derivatives change transformation properties, right? So transformation properties of this combination with A mu, which transform under this, assigned to this, will be assigned to this one. So actually, they live both there, right? Yes, it's also interesting, very interesting representation. This is antisymmetric, F mu nu. Okay. And it's used now in particle physics, actually, this fact that usually people learn, okay, vector is 1/2, 1/2. But it's not so simple. Sometimes something connected with vector through derivatives assigned to another representation in this one. But it's quite important. So thank you for asking. Yeah, more questions? Okay, if not, then we will meet exactly next week, Wednesday, and